Now that we've spent some time looking at how to do all the qualitative ray diagrams, we're going to start doing some of the mathematics involved in curved optics. Sometimes that's done together with a ray diagram, sometimes it's done separately. It just depends on how the problem is written. So to begin with, we're going to look at the equations that we have thus far. In the lens lab that we just did, you should have gotten two different equations. The first one is called the thin lens equation, and that's what's written here. And when you guys did it, it was rearranged for the distance to the image for DI because that was your dependent variable. Here it's the same equation, it's just rearranged for 1 over f, and that is how the equation is normally written. So we have 1 over the focal length equals 1 over the object distance and 1 over the distance to the image. Now, be very careful with signs in this where you're adding things together. The signs are very important. If you mess them up, you're actually not just going to have the wrong sign on your answer, but you may have the wrong numerical value, which is a big problem. So that's our first equation. The second equation is the magnification equation. You should have also found this equation from your thin lens lab. So here you can see that high over ho equals di over do. That was our high ho di do lab. Either side of those is actually equal to the magnification of the image. We saw at the very beginning of our notes for this chapter there was a note under the definition for magnification that said if m is greater than 1 then you have something that's enlarged. If it's smaller than 1 then it's reduced. That's what it was referring to here. As it says with the little note underneath, if you get a negative answer that means that you have an upright and virtual image. Now when I said magnification is greater than 1, it's enlarged, I mean the absolute value of, so don't worry about the negative sign on that. But was the case with the focal lengths having a positive and negative value, the sign on magnification also tells us something about the image as is indicated here. So there are other sign conventions for lenses, and we talked about the focal length already. Another one that's listed here is the distance to the image is positive for real images, negative for virtual images. Sometimes in a problem they'll put that sign on there. They may in a story problem, they may tell you that you have a virtual image and they'll give you that distance, but they won't actually tell you that it's negative. It's for you to know that. That's a little bit of a pain in the rear, but it's okay. It's something you can figure out. And I will actually give you these sign conventions on the test. You just have to be able to apply them. I find it's kind of silly to memorize them, but you can if you want. But you will have those as a reference, but you do need to be able to apply them to problems. So there's our sign convention for lenses, and we're going to do a couple different sample problems here. So the first one, the question is usually asking you about where the image is. That's the most logical question here. So you have an image of a candle appearing 50 centimeters from a lens, and they give you the focal length of the lens. By the way, you'll see a lot of candle problems, and the reason for that is back before they had really cool gizmos like what we use for our lab with the electric box, the electric light box with a nice little arrow that lit up on there. They used to do this lab with candles, and they would basically put candles on a meter stick with a lens in the middle, and they move the candles back and forth and measure the images that they got from that. One problem with that was that obviously as time went on the candle got shorter as it burned, so that was a nice source of error that you didn't have in the lab that you did. So anyway, long story short to say, that's why you're going to see a lot of candles in these problems, because they used to be used for labs all the time. So in this one we're going to look at our knowns and our unknowns. We actually have two parts on this problem. I just have part A on this slide. Our knowns, they tell you how far it is from the lens. It's really important to be able to match up the numbers to the correct variables. So we have our distance to the object, we have our f, and they gave us the height of the object here, the 15 centimeters. So for part A, we're going to find the distance to the image, and then for part B, I believe we find the height of the image. So for part A, finding the distance to the image, you're going to use this equation almost every problem in this chapter. It's the main equation of the chapter, and it's not hard, so that should be a good thing. So all we have to do here is really put in our numbers. Do pay attention to units. They often like to give you some values in millimeters and some in centimeters and things like that. So make sure everything's in the same unit. Doesn't matter which unit you use as long as they're all the same. So here's our setup. You put that in your calculator and you find a distance image there. Okay, so that is part A. Part B, how tall is the image? So we're going to again look at our equation. If they're looking anything about image height, the only place that we have this here in an equation is the Hi-Ho Dido lab. So our equation. So we look at this equation. we put our numbers in. Again, we have simple math. Most of this chapter is very simple math. Last chapter, it really mattered if you were in degrees or radians. Here, you don't have to worry about that at all. And the numbers are all nice, happy numbers, like 10 centimeters, as opposed to last chapter where you had nanometers and just really, really, really small values. So here, you're going to have much happier numbers for your answers. So 10 centimeters is our height. The decimal added there to show 2 sig figs, which I'm sure you all are very concerned about. Sample problem number 2. So here we have a 35 millimeter lens. Lenses, when you think about cameras, camera lenses are usually measured in millimeters. So you think about a 50 millimeter lens, which I believe is the most standard one that you can have. That's what they're referring to is the focal length of the lens inside the camera. So here we have a 35 millimeter lens. So that's our focal length. So we're taking a picture of a car and they give us the distance that we are from the camera. How far should the lens be for the film? How far from the lens should the film be placed? So you need the film to be in the correct spot in order to have a focused image, and that's part of what you're doing in a camera. If you have the old school camera where you have to turn the lens to focus it, that's what you're actually doing, is you're changing the distance between the lens and the film in order to get a focused image. So now most cameras do that automatically if you have a newer one, or if you just use your phone. Phone doesn't even use film, right? Most cameras anymore are digital. So in this case, we've got the good old school film camera, which is really how images should be taken, by the way. And you have the distance to the object is the 5. You have, again, the focal length of the lens. Whenever they give you a number in front of the lens, that is going to be the focal length. So they give you the height of the object. Now we have 3 different units, so it'd be nice if we convert them all into the same one. It doesn't matter which unit you use. If you did this all in millimeters or meters, that would be fine. I thought centimeters would be easy for this problem, so that's what I chose. So for part A, how far from the lens should the film be placed? So we're actually looking for dye, because we want to know the image is going to be formed on the film. So that's where we're looking, why that's dye here. So again, we use our same happy equation, put our beautiful numbers in with the same units, and we get a dye. Notice it's a nice happy number, not a times 10 to the negative 7th or 9th type of value. So there's our distance to the image. Okay, so our part B, what is the height of the image? Height, again, you're going to use our hi-ho-di-do, and we put our numbers in. I'm not going to spend a lot of time explaining this because I think it's pretty self-explanatory. Here you're going to cross multiply and divide, and you get a height of an image. So that's how you do. These are the most standard type of problems that you'll see. Those aren't super hard. Again, sometimes they make you do a ray diagram with the problem. I didn't do that here because you've done plenty of ray diagrams at this point, and you should be able to do that. So here's another one that's a little bit different. So we've got a candle placed 30 centimeters left of the lens. Again, this is referring to that famous candle lab. And the image appears 10 centimeters to the left, 10 centimeters to the left of the lens. Notice that in this case, that both the candle and the image are to the left of the lens. That's different. So we're looking for a couple things here. What is the focal length? What type of image is it? And what type of lens is it? So we really only have to do one thing that's mathematical, and that's to find the focal length. So to do that, they gave us do and die, so we can find F. Sometimes they'll give you hi and ho and make you find, die or do before you can use the thin lens equation. I didn't do that in this particular problem, but that happens occasionally. So in this case, they gave us the numbers directly, so we can put in our numbers to find F. Notice that the negative in front of the 10, I added that when I did the knowns, because I know that if it appears to the left of the lens, it's on the same side of the lens as the candle. When that happens, you should know that you're going to get a virtual image, and that is going to give you a negative distance here. Knowing that, you solve for the focal length, and you get a negative 15. Again, the negative focal length is going to go with the negative distance to the image. Everything's going to, the images then appear on the left. So they asked us a couple things here. Is it real or virtual? You should know that it's going to be virtual because it's behind the lens, and you have that negative value. Is it enlarged or reduced? To answer whether it's enlarged or reduced, you want to look at either hi over ho or die over do. In this case, we have die over do, which would be negative 10 over 30. That simplifies to negative 1/3. The 1/3 is the part that we care about. 1/3 is a smaller number than 1. Don't worry about the sign on the negative 1/3. So if it's 1/3, then it's going to be reduced since that's less than 1. Okay. The third thing is it upright or inverted. you should know that if it's a virtual image, then it's going to be upright. Also, also I said on there the magnification sign is negative, same thing. So if you have a negative net magnification sign, it's going to be upright. If it's of a virtual image, it's going to be upright. Those all go together. What type of lens would this be? In order to have a virtual image where that's going to be on the same side of the lens as the object, that tells you that it's going to be a concave lens. Now, the only place that you can have a convex lens and get a virtual image, if you remember this, is if the object is in front of the focal point. Or I'm sorry, if the object is in front of the focal point, that will give you an enlarged virtual image. Here you have a reduced virtual image, and you know that the object is behind where the image is. So in that case, then it does have to be a concave lens. So that's how we can describe that image. That's a lot more than the first two sample problems in terms of being able to describe the image. That's often asked, so you should be able to do that. So the last one we'll do here is some mirror problems. Again, you have sign conventions. I'm not going to read them all to you. You can look at them. I will give you the sign conventions for the test. Just to me, it doesn't seem like something that is really worth memorizing, but you should be able to refer to these rules and apply them in problems. So here's our first problem. We have a magnified inverted image located at a distance 32 centimeters from a concave mirror with a focal length of 12 centimeters. We're looking for the object distance, and we want to know whether it's a real or virtual image. So first, let's list all of our knowns and unknowns. We do know the distance to the image, and we know the focal length. Should be in the same unit. They're both in centimeters, so that's good. So the first thing they ask us to do is to find the distance to the object. So to do that, again, we're going to use our same thin lens equation. It's called the thin lens equation, but it also applies to curved mirrors. So we can use that here as well. So all we have to do in there is pop our numbers in, refer to the sign convention list and make sure that there's no funny signs. There's none in this problem, so that's good. And we just solve for dou, so that should be easy. Now the last thing we need to know is whether it is real or virtual. This is a concave mirror. The concave mirror, that should be able to tell you that it's going to be real because it's going to be formed in front of the mirror. So, and also the sign on the dou is positive, which tells you that it's going to be inverted. So that tells you that it's real as well. Usually there's more than one logical explanation for that. So that's it for example 1. Example 2, and this will be our last one, we have an inverted image magnified by 2 and the object is placed 22 centimeters in front of a concave mirror. So we need to find the image distance and then the focal length of the mirror. So things we already know. We know the image distance is 22, and this time they gave us the magnification. So they didn't give us all of the other things to do the thin lens equation. We have to actually do something with that 2 to start with. So in order to find the focal length, the first thing we need to do is to find the distance to the image, which we can do with the magnification equation. Remember, m is either di-dou or high over ho. You can use either side of that. Either of those are equal to the magnification. So we do that in order to find di. That's a nice little ratio then. So now we know di, we can go back and use the thin lens equation in order to find f. So there's f for that one. So that actually answers both parts of our question. So I hope you're seeing how these are starting to work together. That's kind of it for lenses and mirrors. They can get, if you were to take this in college, they can get more complicated. We're not going to go there. We're just going to keep it simple as an introductory topic for us. So hopefully that explains things for you. And oh, whoops, I didn't answer the last one. That's embarrassing. There's a focal length, 14.7. Is that it? That's it. Okay. So that is it for mirrors and lenses, and we'll practice these quite a bit. But this is a fairly short chapter, so be looking for a test soon. All right, that's the end.